We have seen that a current-carrying wire can experience a force when placed in a magnetic field. If instead we suspend a loop of wire in a magnetic field, the magnetic force produces a torque on the loop, causing it to rotate. As we will see, this torque is responsible for the operation of a widely used type of electric motor. The figure shows a rectangular loop of wire attached to a vertical shaft. The shaft is mounted so that it is free to rotate in a uniform magnetic field. When there is a current in the loop rotates because magnetic forces act on the vertical sides, labeled 1 and 2 in the drawing. To analyze the forces acting on the loop, it's easier to position our eye directly above the shaft and look down on the horizontal top wire of the loop. The drawing shows the current comes up the left vertical side of the loop, across the top, and then down the right vertical side. By applying right-hand rule 1, we see that there are equal but opposite forces acting on the sides of the loop, so the net force on the loop is 0. However, the net torque on the loop is not, and it tends to rotate about the vertical shaft, here in a clockwise direction. Part A of the figure shows that the torque is maximum when the normal to the plane of the loop is perpendicular to the field. In contrast, Part B shows that the torque is 0 when the normal is parallel to the field. In general, when a current-carrying loop is placed in a magnetic field, the loop tends to rotate such that its normal becomes aligned with the magnetic field. In this respect, a current loop behaves like a magnet, i.e. a compass needle, suspended in a magnetic field, since a magnet also rotates to align itself with the field. Now let's derive an expression for the net torque on the loop. Recall that the torque is equal to the product of the force times the lever arm, F times L. The force on each vertical side of the loop is found by using the equation for the magnetic force on a current-carrying wire, F equals ILB sine theta, which just reduces to F equals ILB since the current in the vertical sides is always perpendicular to the magnetic field. The lever arm is the perpendicular distance from the line of action of the force to the shaft. This distance is given by L equals W over 2 times sine phi, where W is the width of the loop and phi is the angle between the normal to the plane of the loop and the direction of the magnetic field. The net torque is the sum of the torques on each side, which is given by the following. In this result, the product L times W has been replaced by the area A of the loop. If the wire is wrapped so as to form a coil containing a total of n loops, each of area A, the force on each side is n times larger and the torque becomes proportionally greater. The result above has been derived for a rectangular coil, but it is valid for any shape of flat coil, such as a circular coil. In that case, the area A of the coil would be equal to pi r squared, where r is the radius of each coil. The torque depends on the geometric properties of the coil and the current in it through the quantity N times I times A. This quantity is known as the magnetic moment of the coil, and its unit is ampere times meter squared. The greater the magnetic moment of a current-carrying coil, the greater is the torque that the coil experiences when placed in a magnetic field. As one example of an application utilizing the magnetic force on a current-carrying wire, we consider the DC, or direct current electric motor. The electric motor is found in many devices, such as CD players, automobiles, washing machines, and air conditioners. The figure shows that a DC motor consists of a coil of wire placed in a magnetic field that is free to rotate about a vertical shaft. The coil of wire contains many turns and is wrapped around an iron cylinder that rotates with the coil, although these features have been omitted to simplify the drawing. The coil and iron assembly is known as the armature. Each end of the wire coil is attached to a metallic half ring. Rubbing against each of the half rings is a graphite contact known as a brush. While the half rings rotate with the coil, the graphite brushes remain stationary. The two half rings and the associated brushes are referred to as a split ring commutator. The operation of a motor can be understood by considering the following figure. In Part A, the current from the battery enters the coil through the left brush and half ring, goes around the coil, and then leaves through the right half ring and brush. Consistent with right-hand rule 1, the directions of the magnetic forces, F and minus F, on the two sides of the coil are shown in the drawing. These forces produce the torque that turns the coil. Eventually, the coil reaches the position shown in Part B of the drawing. In this position, the half rings momentarily lose electrical contact with the brushes, so that there is no current in the coil and no applied torque. However, like any moving object, the rotating coil does not stop immediately, as it has angular momentum which keeps it spinning. When the half ring re-establishes contact with the brushes, the current once again flows in the coil, and a magnetic torque rotates the coil in the same direction. The split ring commutator ensures that the current is always in the proper direction to yield a torque that produces a continuous rotation of the coil. Here is a short video showing the key components and operation of a simple DC electric motor.